for the win! According to my research, Tenebrio Molitor, or mealworms, can eat polystyrene, also known as styrofoam. This means they could solve a major aspect of environmental pollution. The styrofoam problem increased dramatically during the global pandemic when restaurants turned to takeout to stay in business. I wanted to know if mealworms could live on just polystyrene and whether they could fully develop, breed, and produce offspring in that environment. My research question asks, what are the effects of a polystyrene diet on Tenebrio Molitor development, subsequent breeding behavior, and offspring outcome? According to my literature review, Tenebrio Molitor can digest polystyrene. My hypothesis is that if a population of Tenebrio Molitor is fed an exclusive diet of polystyrene, then it will show similar development and breeding characteristics to a control population fed a normal diet of wheat bran. My independent variables, food source, and my dependent variables are polystyrene consumption, mealworm development, breeding behavior, egg laying, and larvae production. My control population of 500 mealworms was given a standard diet of wheat bran, and my constants for both populations were water and temperature. The materials needed for these experiments are 2 containers of 500 mealworm, 1 sheet of polystyrene, wheat bran bedding, 2 reptile tanks, a lighted magnifying glass, a weighing scale, a spray bottle, and water. The procedures are: count 2 containers of 500 mealworms each, weigh the sheet of polystyrene and record its original weight. Break up the polystyrene and place it into one of the tanks. Place 1 inch of wheat bran in the bottom of the other tank. Place 500 mealworms into each tank. Spray 15 milliliters of water into each tank daily. Monitor the tanks daily and record development. Weigh the polystyrene every 5 days and record. The photos on the slide were all taken from my experiment. The experiment began with larvae. The larvae pupated, hatched into beetles, mated, laid eggs, and the eggs hatched into larvae. At the end of the experiment, new larvae were visible in both the control and experiment populations. This series is a time-lapse of 12 hours in the experiment group. This time-lapse series was taken on day 37 of my experiment. You can see several fully developed darkling beetles as well as the mealworms. The holes you see in the polystyrene are created by mealworms as they eat. These 2 charts are visual representations of my data. I weighed the polystyrene every 5 days throughout the experiment. By day 55, the experiment population had eaten 10 grams of polystyrene, or 41.6%. I monitored mealworm development daily, and I kept a log in the journal of changes and observations. I counted the mealworms at the beginning of the experiment and then counted the surviving mealworms and beetles at the end to show change over time. The control group had 267 live beetles and 35 live mealworms at the end of the experiment. This population had a total of 302 survivors, or 60.4% of the original 500 mealworms. The experiment group had 182 live mealworms and 8 live beetles at the end of the experiment. That population had a total of 190 survivors, or 38% of the original 500 mealworms. My data shows that the polystyrene weight decreased at a steady rate of approximately 0.18 grams per day. Both populations developed into pupae, then into darkling beetles, mated, laid eggs, and hatched larvae. Mating behavior began in both populations around day 40 and was noted from that day on. Egg laying was noted in both experiment populations, and new larvae was visible in both populations at the end of the experiment on day 57. 60.4% of the control population and 38% of the experiment population were still alive on day 57. On day 56 of my experiment, I noticed this beetle laying eggs in my experiment population and took this video. If you look more closely, you will see the ovipositor sticking out over and over, which is how mealworms lay eggs. The purpose of my experiment was to prove that mealworms can survive and breed successfully on an exclusive diet of polystyrene. This is important because my research showed that polystyrene is a significant part of environmental pollution, and that polystyrene pollution has increased dramatically during the pandemic. More people ordered takeout, which increased the demand for styrofoam food containers. Research also shows that polystyrene can give mealworms more protein content, and high-protein mealworms could solve the world hunger problem. The major findings from my experiment are that a mealworm population can survive on a polystyrene diet and can develop into darkling beetles, lay eggs, and produce new larvae. Unfortunately, my findings also show that mealworms in a polystyrene habitat stay in their larval stage much longer than usual and survive at a much lower rate. Mealworms in a polystyrene habitat showed cannibalistic behavior, remained smaller in size throughout the experiment, and had bodies that were softer and more vulnerable than the control population. I would like to continue my study mealworm populations and their ability to survive on polystyrene. In my next study, I would like to add a population that is both polystyrene and wheat bran available. I would also extend my study so that I could follow the next generation of larvae and their possible use as a human protein source. Experiments like mine add to the limited body of knowledge on mealworm populations and the amazing things that mealworms can do to improve our world. This type of work could eventually result in giant mealworm farms that eat our polystyrene waste and produce our food.